Welcome to the Talos principle. Today we will study rendering. This is normally a very beautiful game, but right now we are running the game at somewhat reduced settings in order to demonstrate something. As you already know, pretty much everything you see here is made of textured polygons. If we have a close look at this wall surface here, we can actually see the individual pixels. They are called texels, texture pixels. However, if we take a few steps towards the left, we can see something strange. There is a second set of pixels on top of the wall surface, and these pixels are huge. It is as if the wall has two textures laid on top of each other's. If we take a look around, we can actually see the same happening on many other walls and even on the ground. When playing the game, we don't usually see this because pretty much every game uses bilinear filtering to smooth out the edges between the pixels, but I disabled the filtering in order to show you this. This second texture that is laid over the primary texture is called a lightmap. Its purpose is to darken the underlying texture. Even a game as early as Half-Life supported lightmaps. I was not able to get it to render lightmaps without bilinear filtering, but I was able to demonstrate this case where the lightmaps actually add color to the surfaces. There is no limit to how many textures you can layer on top each other's, other than the available RAM and how slow the rendering becomes. The typical solution is that for each surface material you have a diffuse texture, a normal map, and a reflectivity map. The diffuse texture is basically a photograph, a painting, or some other kind of bitmap picture of the material. The color representation varies, but it is usually some form of RGB. Ideally speaking, this texture is fully illuminated without any shadows or highlights, unlike the example texture shown on the screen. The normal map is a special image that usually appears sort of bluish-purplish. It is not really intended to be displayed as a picture, but instead each pixel contains a mathematical vector that indicates the shape of the surface. It is also called a bump map. If the bottommost texture is called a diffuse texture, the reflectivity map could be called a specular texture. It's usually, but not always, a grayscale texture that indicates how reflective each point on the surface is. The reflectivity map may also be accompanied by a roughness map. For example, Don't Nod's modified Unreal Engine for Remember Me does that. This map contains just a single color channel, and Remember Me actually packs this map into the alpha channel of the normal map texture. This map essentially conveys how polished or smooth the surface is or is not. Some engines replace these two maps with single floating point values for the entire texture. All instances of the same material share these same maps. Then there are 0 or more decals, partially transparent additive or multiplicative textures rendered on top of the surface. Decals are used for doing stuff like stains, deterioration, gunshot holes, spray paintings, and so on. Some engines treat decals as separate polygons, but often it makes sense for the decals to share the normal map of the underlying surface. Then there is the diffuse light map, which is the primary topic of this episode. Different engines use different models for lighting, but the general gist is that lighting is divided into two parts, diffuse and specular. Diffuse lighting is calculated by taking the albedo texel, that is the pixel from the texture, and multiplying that with the illumination value, which is light coming from a light source or reflected by another surface, and multiplying that with the cosine between the normal vector and the light's source direction. This is accumulated from every possible direction where there is something that reflects or emits light. Because this does not depend on the viewing angle, it can all be pre-calculated into a light map, which simplifies the actual rendering into simply multiplying the texel with a luxel. This accounts for both direct and indirect light. Specular lighting is much more computationally expensive because most of this depends on the viewing angle and thus cannot be pre-calculated, at least not easily. It involves many vector calculations and some exponentiations. This accounts only for specular highlights. Adding specular reflections using a cube map is even more complicated, and I have not exactly researched how to do that yet. And then there is the topic of dynamic shadows, ambient occlusions, and so much more. I'm not even sure that I got the specular formula right. I will study it in more detail when the time comes, but for now we will concentrate on diffuse light. First, I will extend the vertices with 2 extra fields. Besides the UV coordinates for the texture, there will now be a second set of UV coordinates for the light map, called LUV coordinates. For the light sources I will add just dummy values there, but for the walls I need some actual values. Let me explain how this works. First, let me dim the lights a bit so we can concentrate better. Now I will spray some light on this wall. It really does look like the lamp is illuminating the wall and the ceiling. Of course, I didn't modify the underlying texture. I sprayed on an overlay texture called Lightmap. I can easily just wipe it clean and start over, because the underlying texture has not been modified. But I do not have 2000 different textures, one for each of these walls. Watch this. On the right side of the screen is what some people call a texture atlas. I prefer to call it a texture canvas though. It is a single texture from which different portions are allocated for different walls. For example, if I paint hello on this wall, you will see the pieces of my beautiful handwriting using just a mouse are being scattered all around the canvas, seemingly with no connection to each other's. To make the demonstration more interesting, I made sure to give each wall a different size light map. Some of these walls are larger than others, but they all share the same canvas. For starters, I will give a constant density for the light map voxels, making them multiples of 16 pixels in each direction. Each light map is part of a big canvas and we need some method to allocate them. So how exactly do we do that? Well, we need to implement the canvas, of course. But before I do that, I will first edit the polygon structure and add 4 extra fields there. I previously had the texture starting coordinates and size. I will add similar fields for the light map. Basically, each texture needs these props, unless 2 of them share the same geometry. Light maps are usually smaller resolution than the texture, so they do need their own coordinates. You will also notice the polygon has 3 vector fields, the normal, the tangent and the bitangent. The code that calculates these vectors was already added in the previous episode, and you saw it briefly on the screen near the beginning of this episode. We will discuss their purpose in more detail soon, but for now let's move on to the canvas. The canvas is a container for pixels. Even though the concept is two-dimensional, we use a single-dimensional vector for it for both efficiency and simplicity. For bookkeeping purposes we also need another vector that tells which pixels are used and which are free. The task of packing varying size objects into varying size holes is actually rather complex. My implementation is very naive and straightforward and not efficient by any means. Because this part of my code falls into the category of writing some code that just gets things done rather than showcasing an exemplary way of doing things, I will just provide this part of the code as is. Basically it just begins from the top left corner of the canvas and looks for the first possible spot that has a vacant contiguous rectangular space of the required dimensions. If there is none, it grows the canvas and tries again. Eventually it is bound to succeed. The next part is where the magic happens and the light map gets calculated. I will first write the code, and once the function is complete, I will explain everything that it does. Alright, this is a background task. STD thread creates a thread which runs on the background. All of this code runs on the background while the main user UI is running. The job of this thread is to generate light maps for every non-emissive polygon, so using this for loop we walk through all the polygons that have flags that indicate it's not a light source. Then for each polygon we calculate 5 vectors. Let me explain how these vectors work. Here we have an example polygon with 4 edges. It is a flat surface somewhere in the space. Every flat surface has also a normal vector. The normal vector is calculated by taking any 2 vectors on the surface and calculating the cross product between them. The normal vector is always at a 90-degree angle to the surface. Always. It is what you need when you want a vector that points straight away from the surface. For example, if the surface is a floor, it points up. Then we have a tangent. The tangent could be any of the edges of the polygon or a cross product between the normal and that edge. Then there is a second tangent called bitangent. You get the bitangent by taking the cross product between the normal and the tangent. For some purposes we may also want to have 2 additional vectors, which I call the antitangent and the antibitangent and the antiband and the antibitangent and the antibitangent. The idea is that all 5 of these vectors are at a 90-degree angle to at least 3 of the other vectors. Thus you get a total of 5 vectors, and each of them is at a 90-degree angle to at least 3 others. Hold on, let me move this closer to the center. The light map is a texture that is laid on the surface. In other words, the surface will be divided into a certain number of luxels. Here, for example, it is divided to 8 by 8 luxels. In order to calculate the color value of each of these luxels, the engine must place a camera on top of each of these luxels, one of them at a time. The camera has a 90-degree field of vision, and it can only capture light from a cone that looks like this. In order to capture light coming from all directions, the camera must be turned. First it will point towards the normal vector, then it will point towards the tangent, and then the bitangent, and so on. When it has rendered all the 5 views, it has successfully gathered illumination from all possible directions. The 5 views are here. For each of these views I use an array that indicates which one of these 5 vectors is the forward vector for the camera, which one points down and which one points right. In the main loop of the lightmap calculator, I go through each non-emissive polygon in the scene. In this loop, we walk through all luxels of the polygon. This is accomplished by using the draw polygon function, but telling it to use for rasterization the lightmap coordinates instead of world coordinates. Every time it calls the plot function we supply here, it does so with different UV coordinates. It also interpolates the world XYZ coordinates just like regular props, so we know exactly where in the world this luxel is. This is where all that C++ magic and refactoring pays off. I didn't have to create any new rendering functions for this. Now once we have the XYZ coordinates somewhere on the surface of that polygon, we place the camera at that luxel on the surface, except that I push it a little bit away from the surface so that it is not inside a wall. Here I go through all of these 5 views. Each view is simply rendered from this camera position. The pixels of the view are collected in the pixel buffer of the view object. Lastly, once all views are rendered, the luxel is given a color from the mathematical mean of these pixels. And now that we have lightmaps, the pixel plotting function that is used for the actual rendering, as well as for the lightmap calculations, can be modified to fetch a luxel and multiply the texture color with the luxel color. This completes the diffuse part of the lighting calculation that I showed earlier. Pixel color equals texture pixel color multiplied by lightmap pixel color. And this is the intermediate result. It is running a bit slow. I am running this footage at a very high fast forward speed, and yet we hardly see any progress on the screen. It's just way too slow. Eventually I did get some white surfaces here. Hold on. I have a 48-thread CPU for a reason. Why use a single thread when we can have 48 of them? Let me change the code a bit so that it maximally utilizes hardware concurrency and divides the work equally between all threads. Alright, it is now noticeably faster. However, one thing that it is also is very dark. If I let it running for a while, it converges towards a result, but it is still very dark. If I made the light sources bigger, then we get more light. It is not an ideal solution, and it is still quite dark. Let me see what happens if we make the light sources brighter instead of bigger. Still not very good. What if we make the lights brighter and bigger? Then we clearly get more light, but we totally lose saturation. Everything becomes grayscale. This is because we are working in true color. True color is a color encoding scheme that has 3 color channels, red, green and blue, and each of these is indicated by an integer in 0 to 255 range. 0 indicates total darkness and 255 indicates maximum brightness. And the thing is, the maximum brightness is actually not very bright. For example, this is the maximally bright, fully saturated blue color. It is impossible for me to convey a brighter blue color in the video. It is just mathematically impossible because of commonly agreed conventions. It is impossible for even you to get a brighter blue color on your screen than this without you manually adjusting your hardware settings. It just cannot be done, and this is not very bright at all. The only way to make it brighter is by adding red and green to it, but this desaturates it. Eventually, as we keep making it brighter, we reach white, at which point it is no longer possible to make it any brighter. Because of these problems, true color is not a very good choice for representing illumination in the program. It is what you have to do when presenting the scene on the screen, but for intermediate calculations we need something different. There are plenty of choices to choose from. For physically accurate rendering, I would need a way to represent an entire color spectrum. I am going to choose a much cheaper solution, which, much like true color, takes advantage of the limitations of human vision. Just use RGB, but instead of integers in 0 to 255 range, we use positive floating point values, which can vary between 0 and about 340 million, with about 7 significant digits. If I am not mistaken, this is more than the dynamic range required to convey differences between the brightness of a single photon and the brightness of 7 billion suns, so it should be enough for our purposes. First, I will convert the texture generator to produce values in 0 to 1 range rather than 0 to 255. The decompose and compose functions are no longer needed. In many places, the multiplication or division by 256 can be removed. Finally, because our view now contains float RGBs rather than integer RGBs, we need to call a separate function to convert the array into true color because our screen can only display true color pixels. This conversion is implemented as follows. For every pixel in the source, we convert it into a true color. This conversion simply multiplies each float value by 256, clamps it into 0 to 255 range, and tags these 3 values together. However, there is a shortcoming in this naive algorithm. Remember earlier when I showed you how the only way to make a maximally blue pixel brighter is to desaturate the pixel? If we just clamp each channel to the 0 to 255 range, we are essentially discarding the brightness information. We can do better. Let me introduce my algorithm, clamp with desaturation. I have previously used this algorithm in a number of my old videos, such as in the OpenGL renderer, the ray tracer, and even in the quick basic star field effect video. It first calculates the brightness of the pixel, or luma, using the I2R recommendation 601 primaries. Then it checks each channel and figures out how much the saturation must be tweaked if the luma is outside 0 to 1 range. I no longer remember how I determined those formula. Finally, it clamps the saturation in 0 to 1 range and adjusts each color channel by that saturation number. This is also a good place to address another problem. Computer monitors are not linear. The RGB value in this color ramp on the screen increases linearly, but the brightness does not. For example, the difference in brightness between these 2 boxes towards the right is much less obvious than the difference in brightness between these 2 boxes towards the left, even though the difference between their value is 34 in both cases. The relationship between pixel value and the perceived brightness follows what is called gamma expansion. Mathematically, it is a simple exponentiation operation where the exponent is the gamma value. The gamma value is typically somewhere around 2. If your renderer plays with linear brightness values, that is perceived brightness values, you need to do gamma compensation or gamma compression. This operation is also an exponentiation, but you need to use the inverse of the gamma for the exponent, that is 1 divided by the gamma. This is what we get. Alright, it is definitely not too dark now. In fact, if anything, it is maybe too bright. Let's make the light sources smaller. Right now the big white light is washing out everything. Now it's maybe too dark. Let's make the lights brighter. This should allow the colored lights to have more impact on the scene. Perfect. Well, it's not perfect, there are quite many visual glitches, but we are getting there. If you notice, we now have shadows. This pillar is casting a nice smooth shadow, as is this little platform here. Alright. Now you may be wondering, why did I create 5 90-degree views pointing up from the surface? Why do we not use a single 180-degree view? The answer is because we use rectilinear projection. This is a 30 degrees field of vision. Look what happens when we enlarge the vision. Yeah, that happens. Distortion happens. Even in this 135-degree view it is evident. Notice how the center 45-degree ring is 3 times narrower than the 45 degrees that are on the far edges of the vision. This is not a bug, it's a feature. It's just how the mathematics works for rectilinear projection. There is a way to make the rings equal width, and it looks like this. It's called fisheye. All the angular bands are now equal width. With fisheye we could even render 180-degree views directly. There is a trade-off. The wall lines are no longer straight. They are slightly curved, most prominently so at the edges of the screen. We also cannot directly do fisheye rendering because we can't just render curved polygons. We will return to this topic in deep detail in a future video, but for now we will focus on rectilinear rendering. 90 degrees is probably the best compromise between these views, so that we still get a relatively good view of the center of the picture while not being totally restricted to a tunnel vision. The bands are not actually equal width here either. Ideally we would gather the exact same number of light from every direction. We could maybe compensate that with some careful mathematics. I tried it for a bit. It involves the tangent function somehow, but I couldn't get it right because my math amounts to basically banging rocks together until something works. So I just pretended this problem does not exist. I think what happens when you don't do it right is that you get these weird diagonal beams from your light sources. But I digress, it could be caused by something else, maybe. I have already spent way too much time on this. There is another issue to consider. Let's make a little experiment. I have here a very powerful incandescent lamp. I'm going to put this wine bottle in front of it, because if I don't do that, the image is going to be completely washed out and there's going to be internal reflections in the lens of the camera, and I don't want that. Next, I have here a rectangular surface which has 2 very important properties. First of all, it is completely flat. And second of all, it is not glossy, it is completely diffuse, which means if I point it at the light source in my room, at any angle, there is no situation where it suddenly becomes very bright. And this is very important for the test. Next I'm going to turn off the lights in my room here. One here and one over here. If I find them, yes. I am still here. You can still just see me because I have a laptop here which shines light on my face. And now I am going to turn on the light. Let's try that again with different camera settings. Okay, so I have the flat surface here, and let's keep it at a constant angle to the light source. If I move it around like this, at a constant distance to the light source, If I keep a constant distance, the brightness of this surface should completely appear constant. No matter where I put it, it should appear at constant brightness. But if I turn the surface like this and keep it still at a constant distance, it should become darker and darker and darker when I turn it, like this. And at this point it should appear almost completely black. It's not completely black because my room is not black, and it is still getting some reflections of the light from the walls of my room. It's not a perfect demonstration, but this shows that the brightness of this surface depends on the angle that it is compared to the light source. In other words, remember the normal vector? It is a vector that is perpendicular to every possible tangent on the surface. Here we have an example ray of light which hits the surface at some angle. The angle between this normal vector and the ray in this example is 50 degrees. To calculate how much this ray illuminates the surface, you take a cosine of that angle. This is actually easier done than it sounds. Just take the dot product between the two vectors and the result is the cosine. Remember that both vectors must be normalized before the multiplication, and that's it. This is the factor by which you must multiply the light coming from that angle. Time to see the code. For each of the 5 views, we add 2 other fields. The normal vector which tells where the camera points to, and a pixel by pixel weights map which indicates the factors that each pixel should be multiplied by, as discussed a minute ago. The process that averages together the pixels will be changed such that it just multiplies each pixel by its corresponding weight. The weight maps are created by taking the dot product between the normal vector and the vector corresponding to this pixel in the view, which can be calculated by reverse perspective projection. The sum of all weights must be normalized to 1 in order to not break the conservation of energy principle. And that's it. And then, just to make the renderer a bit faster, I added some magic code which selects an optimal size for each light map rather than the hard-coded 16 by 16. This part is totally optional, but I decided to show it on screen in order to be honest so that this demo matches the source code I presented. And speaking of demo, here it is. This is the actual speed that my demo runs. It runs at about 6 or 7 frames per second, which is not very impressive, but you have to note that it constantly does lightmap calculation in real time at background on 48 threads, keeping the CPU and RAM pretty busy. I never claimed that my engine is particularly optimized for speed. If I disable the lightmap threads temporarily, the frame rate bumps up to about 16. In any case, if we let the lightmap calculation run for a while, it eventually converges on a result that is looking pretty good. I am using dithering to get more mileage out of the low-resolution lightmaps, just like you remember that the Talos principle did in the beginning of the video, although it used trilinear filtering instead. If I disable dithering momentarily, you can instantly see some jagged edges in the light maps because of the limited texture resolution. Another thing we might observe is these strange patterns here on the floor. This floor is primarily illuminated by the white orb in the space. If we reduce the screen resolution to the same resolution used by the lightmap renderer, that is 64 by 64, we can quickly understand the nature of the problem. This resolution is just so horribly tiny that the source of the light is pretty much reduced into a single pixel. Sometimes the single pixel even disappears from the view entirely. This instability is what produces the patterns in this lightmap as well. To fix the problem, we could give the lightmap renderer a better camera, for example 256 by 256 like this. This is 16 times slower than rendering at 64 by 64, but it does fix the problem. In a video game, you would not have a lightmap renderer running constantly at the background. Instead, you would batch render the lightmaps offline and then just apply them with your product. However, continual recalculation of light maps allows cool stuff like lights that react to dynamic lighting situations. I'm not saying it's an effective way to do that effect, but it can be done. Some of you may be wondering, what is the deal with these strange streaks of light on some of these walls, such as these ones which resemble the patterns on the Jewish Talith? The short answer is, it's a bug in my engine. The long answer is, it's a bug in my engine. I mean, there are some situations where if you position the camera just right, you can see a seam between some polygons, and that seam allows you to see out of boundaries. In this case, the bright white wall in the distance. Here is another position where that problem occurs. I have no idea what causes it. I already verified in episode 1 of the polygon rasterizing series that my engine does not create gaps between polygons as long as the end vertices match. Maybe someday I will figure it out. In any case, that's all I have for you this time. I am kinda tempted to try that specular lighting next, but there are many other topics that I am planning to cover, which I already have proof of concept code written for, so stay tuned. There will be more. Many thanks to all of my supporters or Patreon and YouTube members who provided valuable feedback on this video when I posted previews of it. If you want to see previews of my upcoming content or just to support my work in general, there are many options from the almost zero fees LiberaPay to the popular Patreon and PayPal. Links are in the video description. But the most important support you can give is your thumbs ups and comments, especially comments. Reading your questions and comments is what motivates me best. I read every single comment and also reply most of them, provided that YouTube doesn't put too many hurdles to access it in the first place. As long as you post your comment in the sensible place and not something silly like a reply to the topmost comment, which I would never see in the YouTube studio, it should be fine. This has been an exceptionally labor-intensive series for me to produce, and although it is taxing work, I am happy that I do have ideas that I can put into videos. It's easy to think of video ideas, and I have a backlog of couple of dozen of those, many of which have been suggested by you, thank you very much, but putting those ideas into palatable videos requires creative talent and inspiration that has a fleeting quantity to it. Without any exaggeration, I can say that sometimes one has to wait several years for the production plan to materialize in one's mind. I am glad if I have been of help or inspiration, and I look forward to serve you more in this manner. Be well and healthy, be blessed, and see you again.